Hi, this is a pre-recorded video of our live demonstration that will be presented at ISCAS 2025. We took inspiration from the human brain to develop a spiking neural network-based smart watchdog for monitoring control flow in a RISC-V processor. The smart watchdog can monitor program execution of any C code compiled and doesn't require any hardware changes, and is also smart enough to work alongside the existing RISC-V trap handler and can detect faults that are not detected by the RISC-V itself. For this live demonstration, a realistic motor control task is executed on the RISC-V CPU, and the smart watchdog monitors the RISC-V on hardware in real time and makes decisions on control flow. The RISC-V uses GPIO, timers, PWM, and interrupts to control the speed and direction of a motor based on user input and speed feedback generated by the rotary encoder. Faults can be injected into the RISC-V, and the smart watchdog response can be observed. A Python-based GUI provides detailed information about the demo and also allows operation from there. This is the hardware setup for the live demo, and we will now take a look at it in more detail. Okay, so we've powered up the demo and programmed the FPGA using the Vitis IDE. Currently the RISC-V processor is in reset, and we can bring it out of reset by flicking this switch. So now the processor will be executing our C code that we compiled in order to control the speed and direction of the motor. Let's first demonstrate motor control. You can observe the actual speed of the motor following the set point. And the speeds are capped between 2000 and 4000 RPM. We can also change the direction of the motor. And we can verify the speed of the motor using a digital tachometer. We have an oscilloscope hooked up to the PWM signal from the RISC-V, so we can observe it on the oscilloscope. Now that we've covered motor control, let's take a look at injecting some faults into the RISC-V application and see the smart watchdog in action. Faults are injected into the program counter register of the RISC-V during program execution to create control flow errors. Faults are set up and injected using the fault setup buttons and the fault injection control buttons. The smart watchdog response can be observed here on these two LEDs, with a green light indicating no faults have been detected and a red LED indicating that a fault has been detected. Let's see the watchdog monitoring the RISC-V in real time. When we trigger the fault injection logic, the RISC-V instruction data is stored in this buffer, and the smart watchdog component reads the instruction data and classifies it, checking for control flow errors. So let's start the motor. Let's trigger the fault injection logic with no faults set up. So here you can see the smart watchdogs detected no faults. That's what we expect, as no faults were physically injected. This time let's try a stuck at 1 on a higher bit such as bit 8. So here you can notice an audible noise difference in the motor, and our smart watchdogs picked up the fault. If we check the motor speed, you can see it no longer matches the RISC-V calculation, and the program is actually non-responsive. We can't change direction or even stop the motor. We need to reset the RISC-V in this case and clear our faults. You'll notice that the trap handler LED in the RISC-V is not illuminated, and that means that there was no trap triggered in the RISC-V. That last stuck at 1 was not detected. Let's clear fault setups and start the motor again. This time we can try multiple bit flips and inject. So straight away the smart watchdogs recognize the fault, but it's not entirely obvious that a control flow error has occurred, as the motor still seems to respond as normal. Let's remove the fault. In this case, it's hard to see the actual control flow error happening on this PCB, and we created a custom Python-based GUI for this reason. So let's check that out. So here's the Python-based GUI. We've moved the hardware down to the corner of the screen. We have a motor control area and a fault control area and a smart watchdog monitoring area, the same as before, except the monitoring area provides much more information now on the GUI. Let's start the motor. We can also now, as well as controlling the speed through these buttons, we can now load in speed values directly. Let's repeat the same as before and classify some instructions with no fault setup. And let's stop the motor. So here you can see the smart watchdog classified 996 instructions and all contain no faults. As well, you can see on the board the green lights lit up for no faults detected. Let's start the motor, clear the faults, and this time let's inject a bit flip and repeat the process. So you can see the smart watchdog has detected a fault, and this is also shown on the GUI here. Let's first of all clear the fault and stop the motor. We'll have to reset the RISC-V as it's unresponsive. This time one fault was detected, but we can go a step further and show more information on this by enabling the instruction info and the spike plot. The information inside the FPGA is now sent to the Python GUI over UART so that we can analyze it in more detail. As we're now streaming more data over the UART, and UART being a slow protocol, we can actually reduce the number of clock cycles worth of instruction data written from the RISC-V to the buffer. Currently it's 4,000, but let's reduce this. Let's start the motor and set up some random faults. And inject them. So the faults have caused the motor to stop, and you can see here the data upload from the UART does take a while. Once complete, we can see the RISC-V actually doesn't respond to GPIO anymore. We can't start the motor, so we're going to have to reset it. Let's remove the injected faults and clear the fault setups. We can see from the 750 clock cycles of RISC-V data stored in the buffer that there was 173 instructions executed, and the smart watchdog classified these in real time on FPGA. 162 of these were executed normally, where 11 of these instructions contain control flow errors. And we can observe them in more detail in this instruction analysis area. There was 162 instructions executed with no errors. The selected instruction number 2 is a branch, if not equal. And we can check this by looking at the disassembled code file generated by the RISC-V's compiled toolchain. We can see that at instruction memory 580 hex is in fact a branch if not equal instruction, and the 32-bit instruction register value can be seen there. You can see that in this case the branch was taken and the target address should be 588, and this is in fact where the program counter continued execution at. There was no control flow error in this instruction, and the SNN has also agreed with that, as that's what the classification was. We can look in more detail at the data for every clock cycle that was in the instruction buffer. You can see the instruction register, program counter, and other registers, including the states that the CPU is in. So here the branch state indicates that the processor is evaluating the branch condition, and the branched state indicates that the branch is being taken. The remaining dispatch states is then the CPU flushing out the prefetch instruction buffer, and execution is then resuming at address 588. The features extracted from all those clock cycles worth of data are highlighted here, and they are the result of passing that information in the buffer through the feature layer to capture these 16 features. We can also then plot the spiking activity from inside the SNN of the smart watchdog, and you can see the input spikes, the hidden neuron spikes, and the output spikes as well. Our SNN has two outputs. neuron 0 for no fault in that instruction, and neuron 1 for a fault detected in that instruction. And whichever neuron spikes the most is the class for that input data. You can see neuron 0 spikes more times than neuron 1, and that indicates that the SNN has detected no fault. We can see our spike encoding here, and we can get an image brought up of our scheme. You can see if a feature is a logic 0, 2 spikes will occur out of the 10 time steps, and a logic 1 would be 8 spikes out of the 10 time steps. We can then see execution continue by looking at the next instruction, which we know is at 588. So the program counter has successfully branched to here and it has fetched this instruction, which happens to be a load byte unsigned. This is a non-transferring control flow instruction, so the program counter should increment by 4 bytes and fetch the next instruction at 58C, which it does here. You can observe this time the CPU is not taking a branch. It is obviously loading from memory, so there's a memory request cycle and 3 cycles for a memory wait, and then a dispatch for the next instruction. The features again are different, and they match up to those where they correspond to that instruction buffer. Our input spikes then match the features accordingly, and our output spikes again verifies that neuron 0 has spiked the most, indicating no fault detected by the smart watchdog. We can then select the instructions that had faults, and we can cycle through them as well. Let's pick one, and let's bring up our text file. So we can see this instruction had a control flow error. It was a jump and link instruction, and the program counter was 560, which is here. It is in fact a jump and link, as you can see in the disassembly file with the opcode or the instruction also matching the GUI instruction. The target address of the jump and link should have been AB0, which we've computed here. However, you can see that the program counter actually got updated with 8B0, which is definitely a control flow error. Let's look at this in more detail. You can see the hex value AB0 contains bit 9 as a 1. However, 8B0, bit 9, is actually a 0, and that was because we injected a stuck at 0 on bit 9 in this fault. We can also then plot this, and you can see the input and the hidden layer spiking activity is different, but in this case neuron 1 has spiked more times than neuron 0, indicating that the SNN has detected a fault. So that concludes the demo video, and thanks for listening.